Hello everyone, my name is Dr. Jyoti Tiwari and I'm a postdoctoral fellow in the Department of Earth Sciences at IIT Bombay, working under the supervision of Professor Soumyajit Mukherjee. Today I'd like to present our work on seismotectonic model of the Kullu-Larji-Rampur window in the Northwest Himalaya. Throughout this presentation, I'll walk you through the major investigations and discuss its implication in understanding the active deformation and seismic risk in the Northwest Himalaya. The topic of my talk today is Seismotectonic Model of the Kullu-Larji-Rampur Window, Northwest Himalaya, a study based on structural analysis, seismicity, and localized stress. It deals with the structural and seismic aspect of a window to assess tectonic activity. Why a tectonic window? The Northwest Himalaya is a complex terrain and it exposes a rare antiformal structure that is a window. It brings out the deeper geological formation and help us to understand the Earth's structure and tectonic history by exposing the deeper geological formations. The article was published in Himalayan Geology in 2024 and was co-authored by Dr. S.S. Bhakuni, Professor Pradeep K. Goswami and Dr. Anil Tiwari. The Himalayan fold thrust belt is known for its intense tectonic activity and complex geology. In Himachal region, this complexity is further marked by the presence of a tectonic window, that is Kullu-Larji-Rampur window. These window exposes the deeper structure that lies beneath the crystalline nappe. Our goal here is to understand the structural pattern, the seismicity and localized stress combined in this region. The Himalayan tectonic window comprises of lesser Himalayan sedimentary sequence. Extensive movement of crystalline thrust sheet towards south led to the exposure of this tectonic feature, that is an erosion parallel window, Kullu-Larji-Rampur window. Now let's move on to understand the geology of the area. Himalayan fold thrust belt has been studied by many pioneer workers on regional scale as well as on large scale at structural and geomorphological aspect. Also, the Himachal Lesser Himalaya, that is distinguished by the presence of metasedimentaries and metavolcanics, has also been studied by many workers. But this study has been concentrated majorly to the thrust zone or a local scale. The window, being an active structure, has not been studied for seismotectonic evolution. This is the geological map of the study area. It is a doubly plunging antiformal window that is bounded by Jutok thrust in the northern limb, Chale thrust in the southern limb. In the hinge zone lies Pandal granite gneiss, and window is uncovered by metabasics and metavolcanics and some associated sedimentaries and dolomitic rocks. With this overview in mind, let's look at what we observed in the field and how deformation is recorded in the rocks. This is the Jutok thrust. This is the hanging wall and this is the footwall of Jutok thrust. The hanging wall predominantly comprises of mylonitic gneisses and footwall comprises of Rampur quartzites. Notably, in the footwall block, the bedding foliation of quartzite exhibits a steep dip of 70° towards northeast. However, as one approaches closer to the thrust zone, these beds gradually become subhorizontal, that is 10° towards northeast. This observed variation in bedding orientation suggests a significant deformation gradient associated with the proximity of the thrust zone. How can variation of bedding orientation depend on tectonic forces? The variation in the bedding orientation can be due to some past tectonic activities and can be a key feature to understand the past active tectonics. This variation can be due to some folding, faulting or tilting that can be influenced by a tectonic force. For example, a steep bed can be due to a compressional force leading to a folding, and abrupt change in bedding orientation across a fault line can be something related to a fault. In the hanging wall of Jutok thrust, we observe well-developed mylonitic foliation within gneissic rocks accompanied by chlorite sericite cyst zone that is indicative of retrograde metamorphism. Brittle structures along with some crenulation cleavages and minor faulting is also observed in the study area. These crenulation cleavages has hinge line aligned parallel to the strike of the country rock. Also notably, the frequency and tightness of these crenulation cleavages increases as we go towards the base of the hanging wall block. This complex structural overprint reflects a progressive deformation history with initial ductile shearing followed by brittle deformation along the Jutok thrust. The base of the hanging wall block of Jutok thrust exhibits asymmetric folding, indicative of an up-tip sense of sharing. The axial plane of these tight folds are dominated by penetrative foliation, and additionally some presence of sleeken sides, layer parallel stretching is also observed in the study area. The Satluj River flowing in northeast-southwest direction transects the Jutok thrust, dividing it into two segments: eastern segment, that is the left bank of Satluj River, and the western segment, that is the right bank of Satluj River. In the eastern segment, that is the left bank of Satluj River, the hill slopes exhibit surface traces of brittle thrust and normal fault imbrications aligning with this perennial brawny khud, which is a tributary of Satluj River. This alignment suggests recent tectonic activity influencing the Jutok thrust. However, no such influence of any tributary or uplifted terraces or any topographic break is observed in the western bank, that is the right bank of Satluj River, indicating the right bank of Satluj River to be a dormant portion. These structural complexities align with modern seismicity observation. Now, let's move to the seismicity. In this study, we analyzed localized stress behavior of seismically active region by examining some background seismicity. The B value, a parameter in the Gutenberg-Richter relationship, typically averages around 1 in a tectonically active regime, but can range from 0.4 to 1.5 depending upon the regional complexities and heterogeneity. Our analysis, incorporating some past earthquake as well as recent tectonic events, yielded a B value of 0.76 plus minus 0.04. Additionally, the annual A value of 3.11 and the magnitude of completeness of 2.7. This magnitude of completeness indicate that the earthquake above the magnitude of 2.7 can be reliable for our study and can be suitable for further seismic parameter analysis. Why the B value is significant for assessing the seismic hazard potential? A lower B value, typically less than 1, indicate a higher stress accumulation and more frequent earthquake, while a higher B value conversely indicate smaller earthquake and very less stress accumulation in the area. Thus, assessing a B value can help in categorizing seismic hazard area. This is the depth-wise estimation of B value, revealing significant variability beneath the Satluj River Valley. At the depth of 10 to 13 kilometers, it exhibits a very less B value of less than 0.7, which is indicative of elevated stress accumulation. This depth range coincides with the zone where most moderate to strong co-seismic ruptures occurred in the northwest Himalaya. An abrupt increase in B value after 13 kilometers indicate it to be a transition zone between brittle to semi-brittle. Also, this 10 to 13 kilometer zone is known as the asperity zone. The estimated DC value, that is fractal dimension value, to indicate the clusterization or randomness of the earthquake data was also calculated, and we got a DC value of 1.46 plus minus 0.04, that is comparatively very low as compared to other part of the northwest Himalaya, indicating that the earthquake is more clustered rather than random in the study region. Both the B value and this DC value trend indicates ongoing stress accumulation in the region that is driven by some ongoing northward convergence in the Kullu-Larji-Rampur window. We have analyzed over 1300 seismic events using ISC and USGS catalog. Mapping B values and DC values across the region help us to identify where stress is building up the most. So, how to connect this seismic and structural data? Observations indicate that the northwest part of this Kullu-Larji-Rampur window lacks number of earthquake, that is, it exhibits minimal earthquake in the area. However, maximum earthquake in the window are accumulated in the southeastern zone of this window. Additionally, this pattern is also consistent with other part of the northwest Himalaya, suggesting varying stress accumulation across these areas. Integrating field observations and seismic data suggests that the northwestern margin, that is the Jutok thrust region of this Kullu-Larji-Rampur window, is undergoing active uplift. This uplift is likely driven by shortening, that is along the hinge zone of this antiformal Kullu-Larji-Rampur window. In conclusion, active deformation is ongoing within the Kullu-Larji-Rampur window, and there is significant uplift and fault reactivation mainly in the hinge zone, that is antiformal hinge zone. Also, integrating the geological mapping with seismic data can help us in assessing the seismically active region throughout the Himalaya and can help in seismic hazard assessment as well as planning for seismic potentials. I would like to acknowledge Vadia Institute of Himalayan Geology, Dehradun, Kumaon University, Nainital, Department of Science and Technology, and University Grants Commission for the research work. Thank you all for your attention. Any questions and suggestions are welcomed in the email ID provided below. Thank you so much.